So, good morning everyone. Can you hear me fine? Perfect. Really nice to see you. So, welcome to this talk on a crystal ball. A crystal ball that will help us to not only identify, but also to prioritize technical debt. So, let us jump right in and see what this is all about. And my starting point here is Martin Fowler's well-known definition of technical debt. And I want us to focus on the key aspect here. And the key aspect of technical debt is that, just like its financial counterpart, technical debt incurs interest payments. And this is something I've found that we in the software industry seems to sometimes misunderstand and sometimes misuse. And as a consequence, technical debt, the very concept, is not as useful or helpful as it could be. Let me show you an example on that. So, what's going to happen now is that I'm going to do a small test. Or rather, you are going to do a small test. You weren't prepared for that early in the morning, were you? But here we go. What's going to happen now is that I'm going to put up a piece of code here. And your task is to judge the quality of that piece of code. Are you ready? You do look ready. Here we go. Have a look at this beauty. What do you think about that? How many think that this is great, fabulous code? Not so many. How many would let it through a code review? Wow, it's really just me. Of course, this is not good code. This is not the kind of code we would like to see. And we would, of course, never, ever write code like this ourselves. Never. But is it a problem? Is it technical debt? Without more context, we just cannot tell. Because it's not technical debt unless we pay interest rate on it. An interest rate, interestingly enough, is a function of time. So that means in order to decide if this is technical debt or not, we would need a time dimension into our code. Where can we get such a thing? In a few minutes, I'm going to show you one possible way. But before we go there, I would like to share a little story with you. Now, as part of my day job, I go to different organizations and I analyze their code and try to come up with some recommendations on how they can reduce their technical debt. And last year, I visited one organization that prior to my arrival had used a tool capable of quantifying technical debt. So they had taken this tool and thrown it at their 15-year-old codebase. And this tool reported that on your 15-year-old codebase, you have accumulated 4,000 years of technical debt. 4,000 years, right? Just to put that into perspective, 4,000 years ago, that was here, when Moses parted the Red Sea. So 4,000 years of technical debt, I mean, it may well be accurate, but it's not particularly helpful. I mean, where do you start if you want to pay it off? Is all debt equally important? Besides, I think it's a mistake to try to quantify technical debt from code alone. And the reason I think that is because most technical debt isn't even technical. And again, this is something I find over and over again as I work with different organizations, that we developers, we tend to mistake organizational problems for technical issues. And the consequence is that we start to treat the symptoms instead of the true disease. So let me give you some quick examples on when that can happen. Perhaps you have experienced this yourself. You know, you start out on a new assignment or a new job, and the first day you get there, someone takes care of you, show you around, and they talk a bit about your system you're supposed to build, and they tell you that, hey, watch out for this part of the code over here. It's really, really nasty. You don't want to go there, right? It's really hard to understand. You recognize that? Or maybe maybe I've seen my personal favorite. This is one I really love. Come across it several times. So let's see if you have heard this one. Yeah, we spend a lot of time merging our different feature branches. We need to buy better merge tools. As you will see, tooling might not be the problem. There might be a social side to that. And we're going to cover that later today. But I would like to point out that I think the main reason that we keep making this misattribution is because the organization that builds the system is invisible in the code itself. And this is really, really unfortunate because there is a very strong link between technical debt and organization behind the code base. And I'm pretty sure that we will never be able to successfully address technical debt unless we take a holistic view of the concept. And that holistic view has to include a social and organizational side. So let me try to put all this together. So far, I pointed out a number of issues with technical debt, and what I did now was that I put together a wish list on the kind of ideal information that I think we will need in order to successfully address technical debt. So let's have a look at that. The first thing we'd like to know is, given all our code, where's the code with the highest interest rate? The second thing we would like to know is, how does it look from an architectural perspective? Do we work with or against our architecture, which is actually quite common? And finally, and perhaps most important, how does it look from an organizational perspective? Are there any team productivity bottlenecks? You know, those parts of the code where 5 different teams continuously have to coordinate and synchronize their work. Now, I hope you all agree with me that this is information that's useful to us, that can help us do a better job. However, I would like to point out that none of this information is available in the code itself. More importantly, we lack a time dimension and we lack social data. So, how can we get that kind of data? Where's our crystal ball? It turns out you all already have one. We're just not used to think about it that way. I'm talking about this, our version control data. Our version control data is an informational goldmine. And I find it fascinating that version control data, it's something that we have used traditionally as more or less a complicated backup system and occasionally as a coordination tool. And then almost as a side effect, we have built up all this wonderful behavioral data that's just waiting for us to inspect, mine, and get information. So this is just a simple example from Git. And you see that we get a time dimension with version control. We know exactly which part of the software that were changed at which point in time. And even more importantly, version control data is social data. So that means we know exactly which developer that worked with which parts of the code over time. So let's embrace version control data as our crystal ball and let's see where it takes us. And let's start by trying to uncover the code with the highest interest rate. And the technique I use for this is something I call hotspots. Now, I'm going to walk you through this visualization in a minute. This is a hotspot analysis of a well-known, mature Java codebase, Tomcat. How many of you have worked with Tomcat? Wow, almost everyone. How many have looked at the code? So 10, 15 people maybe. Cool. So let's see what we see here. So this visualization, have a look at those large blue circles, the ones that blink on screen right now. Each one of those represents a folder in that codebase. So this is a hierarchical visualization that follows the folder structure of your code. It's also an interactive visualization, which is important once you get to larger systems. So that means you can zoom in on any level of detail you're interested in. And when you do that, you will see that each file is visualized as a circle. And you will see that the circles have different size. That's because the size of the circle is used to express something called the code complexity. That is, how hard is this code for a human to understand? Now, how do you measure a thing like code complexity? Well, we have a bunch of different ways of doing that. You might have heard about things like cyclomatic complexity, cognitive complexity, nested function complexity, and so on. And what they all have in common is that they are pretty bad at actually predicting complexity. So what I tend to recommend is to use the simplest thing that could possibly work, and that is the number of lines of code. Yes, it's a lousy complexity metric, but it will give you an indication, and it's simple and language neutral. Besides, that's not the interesting dimension. The interesting thing when it comes to complexity is to know if this complexity actually affects us. Is this a part of the code where we need to work? And this is data that we can pull out of a version control system. So we can look at how often do we actually work in each part of the code. We calculate the change frequency of the code. and use that as a proxy for interest rate on any technical debt. Now, when we combine these two dimensions, we're able to identify complicated code that you have to work with often. And those are our hotspots. So let's return to Tomcat. As you see here on the hotspot analysis, the hotspots make up relatively few parts of the code. There are not that many of them, right? Now, what does a hotspot actually tell us? First of all, a hotspot doesn't say it's a problem necessarily. It just tells you that this code is a little bit extra important to you. So the hotspots are the part of the code where it's really, really, really important that the code is easy to understand, easy to evolve, and easy to maintain, because that's where you spend most of your time. In practice, more often than not, the opposite is true. And that tends to make hotspots excellent refactoring candidates. And there's a fascinating reason why that works. So, how many of you have read any work by George Orwell? Yeah, cool. So those of you who have read George Orwell, you might remember that he once said that all code is equal, but some code is more equal than others. Now, what do I mean about this? Well, have a look at the following graphs. Each one of those graphs show exactly the same thing. Here on the x-axis, you have each file in the system, and those files are sorted according to the change frequency. That is, how many commits have we done to that file. And the number of commits is what you see on the y-axis. Now, have a look at those three examples on top there. They show three radically different code bases, developed in different programming languages, targeting different domains, different lifetime spans, different developers, different organizations. Everything is different. Yet, do you see any similarities in the patterns? That's right. They all show exactly the same distribution. They show a power law distribution. And this is something I've found in every single code base that I've analyzed. This seems to be the way that software evolves. And this is important because it gives us a tool to prioritize. Because what this means is that most of our code will be here in the long tail. That's code that's rarely, if ever, touched. And most of our work will be done in a relatively small part of the code base. So that's the part where we will prioritize improvements and be pretty sure that we get a real return on that investment. And hotspots point you to precisely those parts that matter. So hotspots are a really, really good starting point. But sometimes they are not enough. And I would like to show you an example on when hotspots don't work. Now I'm going to switch codebase. I'm going to switch codebase to a codebase that I think a lot of you actually have running on your laptops right now. The .NET Core Runtime from Microsoft. Now, the .NET Core Runtime is a fascinating piece of software. So when I did this hotspot analysis, I think it's like 6-7 months ago, but it looks pretty similar today. Most of the hotspots were here. They were in a cluster inside the JIT package. Ah, that's the just-in-time compilation support. Interesting. But even more interesting is this satellite that we see here, this satellite hotspot. This is a file called gc.cpp. That's the .NET garbage collector. Interesting. Now, gc.cpp might look quite innocent here on screen, but that's just because the scale of .NET Core. .NET Core is a big code base, so what you see here on screen is almost 4 million lines of code. And gc.cpp is a pretty big file. How big? I don't really have any idea, so let's look it up on GitHub. Here's what it looks like. All right, so it's so big that GitHub fails to visualize it. We're using a syntax markup, so we need to look at the raw file. And when we do that, we find out that gc.cpp consists of 37,000 lines of C++. 37,000 lines of C++. Now, let me tell you, I used to be a C++ developer. I did C++ for more than 10 years. And I know what you all think. Those are 10 years I'll never get back. But that's not like my main point, right? My main point is that I have a lot of respect for 37,000 lines of C++. It's quite scary stuff, right? That's the stuff nightmares are made of. And besides, how useful would it be to know that gc.cpp is a hotspot? Let's say I get to your organization and I analyze your codebase and say, hey, look, I found your worst maintenance problems. You just rewrite this file with 37 lines of C++ and all your problems will go away. Would that be helpful? No, not really. How do you react on that information? The answer is you don't. You need much more detailed information. So what I do when I come across those large hotspots is that I use the following technique. I take that large file and then I parse it into the different functions, and then I look at the commits in which functions do they hit over time. So that let me calculate hotspots on a function level. Let me show you an example from gc.cpp. Here it is. So these are the hotspot level functions inside gc.cpp. And you see that the number one hotspot on a function level is something called grow brick card tables, whatever that is. We see that it's a pretty big function, 332 lines of code. It's quite a lot for a single function, isn't it? But it's much less than 37,000 lines of code, which was the size of a total file. And it's definitely less than 4 million lines of code, which was the size of a total system. So more importantly, we are now at a level where we can act upon the information and do a focused refactoring based on how we actually work with the code. Now, I'm going to come back to the hotspots, but before that, I would like to give you a book recommendation. This is a book called The Challenger Launch Decision, written by Diane Vaughan. And it's the best book I know on how organizations fail. Now, Diane Vaughan is fascinating because she's not a software developer. She's not a programmer. She's a sociologist. And she studied the Challenger launch accident. So how many of you remember the Challenger accident? Wow, so like half of you, right? So let's cover this briefly. This is the Space Shuttle Challenger on its final launch back in 1986. And this is the actual space shuttle. The white large object that you see here in front of you, that's something called a solid rocket booster. Now, those solid rocket boosters, those are huge, huge rockets. In fact, they are so big that they are delivered in 3 separate segments that are then assembled before launch. Now, if you look at that solid rocket booster, you see a puff of gray smoke here. You see it? It's not a good thing. Not supposed to be there. So what actually happened here was that one of those solid rocket booster joints failed to seal, and as a consequence, hot rocket gases were able to escape and impact and compromise the structure of the whole space shuttle system. And once it got into the air, it just disintegrated. Now, what Diane Vaughan tells us in her book was that already back in the 1970s, during the early design of the space shuttle system, the early design tests, they show that those solid rocket booster joints, their actual performance deviates from their predicted performance. That's not a good thing if you want to fly rockets. What do? Well, if you're NASA, it's easy. You just form a committee. So they did. And they discussed the problem and decided to pass it off as an acceptable risk. Years later, in the early 1980s, during the first in-flight tests, again, the first tests showed that the actual performance of those solid rocket booster joints deviated from the predicted performance. Again, it was discussed and passed off as an acceptable risk. And it went on and on like that for years, before on the very eve of the launch, there were some very serious concerns raised by some engineers due to the unusually cold temperatures in Florida at that time. And again, the problem was discussed and passed off as an acceptable risk. And the consequence was a tragic loss of human lives. This is what Diane Vaughan calls the normalization of deviance. That each time we accept a deviation, those deviations become our new normal. We get a new point of reference. And what I find so fascinating about that is that the normalization of deviance has nothing at all to do with spaceships. It's all about people. People like us who develop software. And we have plenty of normalization of deviance within the software industry too. So think back to this file with 37,000 lines of C++. How do you get there? Well, let's say that you inherit a file with 5,000 lines of code. At first, you might not be that happy about it, but if you spend enough time with it, soon you start to feel familiar with the code. And I mean, besides, you have 5,000 lines of code, so what difference does 100 extra lines of code do? So soon you have 6,000 lines of code, then you have 7,000 lines of code, and so on. And we need a way to detect, stop, and fight the normalization of deviance. Here's one technique I've been using for that. This is something I call complexity trends, and they're pretty simple to calculate. All I do is I go to my version control system for each hotspot, and then I pull out all historic revisions of that code, and then I measure the code complexity using any metric you want. It could be cyclomatic complexity, whatever, and plot the trend over time. So that's the red line here. The blue line is just a count of the lines of code as a reference. Now, what I find so fascinating about complexity trends is that all systems tell stories. We just need to learn to read them. So let's have a look at this example. This is actually a piece of code where I worked myself too. So what happened here was sometime in 2016, we did a refactoring. And you can actually detect that small improvement, right? A slight decrease in complexity. But we probably failed to address the true root cause. So pretty soon the complexity keeps creeping back in again. And here, early 2017, there's a steep increase in complexity, which is a warning sign. It's a sign that we might have to take a step back and investigate what's actually going on here. The normalization of deviance is one of the reasons why whistleblowers are so important to an organization. And I have found that complexity trends are excellent whistleblowers in code. Now, to sum up my hotspots. Hotspots help us identify the code with the highest interest rate. And the reason hotspots work is because all code isn't equal. Now, let's continue by talking a little bit about how we can use the same techniques to evaluate our architectural patterns. And as you all know, you cannot really talk about architecture without mentioning art. Now, how many of you recognize this painting? No one. That's really, really good because it doesn't exist. This is something called a liquid crystal light projection done by the artist Gustav Metzger. And what's so fascinating about this crystal light projection is that it changes, it morphs all the time, right? So this artwork looks completely different today than it did yesterday. And what I find fascinating is the way it changes. Because the way it changes is that it necessitates the destruction of an existing form for the creation of a new form. And what I like about that is because that's exactly the way software is supposed to evolve. And it's also a reason I like hotspots, because they make it clear that a codebase is never done. Successful code will evolve, it will change, and that's actually a good thing. It means we have users, right? However, the reason I say code is auto-destructive is because changes and new features tend to become increasingly more difficult to implement over time. And some systems, they just reach a tipping point, and beyond that point, they become virtually impossible to maintain. So, how can we detect that? How can we detect those parts of the code? Well, we have hotspots, right? So hotspots might work on a function or a file level, but in a large system with million lines of code, or maybe a distributed system like a microservice system, we need a higher level view. So one concept I've been using is the following. Instead of focusing on individual files, what I do now is that I take a group of files, maybe even a whole folder of files, and then I map that to a logical name, a logical component. And what I do then is that I just aggregate all version control activity on any file within that logical component. I aggregate it and sum it up, and that let us calculate hotspots on an architectural level. And most importantly, you can use any grouping you want. The important thing is just that your logical components carry a meaning from an architectural perspective. So they should have some architectural significance. Now, using this data, we can start to ask the right questions. Let me show you an example from a service-oriented architecture. Now, this kind of data can help us answer one of the big questions we have around microservices. And this is a really big question, because this is a question that, you know, if you look at internet, flame wars have been fought about it, friendships have been ended. And that question is, how big is a microservice supposed to be? 100 lines, 1,000 lines, 2,000? Well, we all know it's kind of pointless and misdirected to reason about microservice size in terms of lines of code. What we're after is business capabilities. We want each service to implement a single business capability. So let's see how we can supervise that. So what I do now is that I take all files that belong to a single service, aggregate the contributions to all of those, and calculate hotspots on a service level. And here's an example from our real-world microservice system. And we see that the number one hotspot is something called a recommendation service. Now, we can also calculate complexity trends based on those boundaries. And when we do that, we see that this is some piece of code that seems to have evolved rapidly and then stabilized at a very high complexity level where it keeps changes all the time. And it's around 5,000 lines of code. Now, using this data, we can start to ask the right questions. We can ask questions like, does this service with 5,000 lines of code that changes at a rapid rate, does it really implement a single business capability? Or is it maybe a service that has 2 or 3 or 4 different responsibilities and would be better off when split into multiple different services? But we can do much more once we embrace version control data. And I want to show you one more thing. And in order to do that, I want to introduce a concept called temporary coupling. Now, temporary coupling is different from the way we typically talk about coupling, because temporary coupling is invisible in the code itself. It's something you can only detect from the evolution of the code. Here's how it works. Let's say we have a simple system here, just 3 different subsystems. And the first time I do a change to the system, I modify the fuel injector and the diagnostics module together. The next time, I modify something else. The third time, I'm back to modify the fuel injector and the diagnostics module. Now, if this is a trend that continues, there has to be some kind of relationship between the fuel injector and the diagnostics module, right? Because they keep changing together over time. They are coupled in time. They have a temporal coupling. So let's see how we can use temporal coupling to evaluate our architectural patterns. I'd like to start by discussing a layered architecture. And layered architecture are quite popular. And what I find fascinating is that when I get to a client and ask them what kind of architecture you have, and they say, oh, we use a model view controller. And they might even draw something like that. However, then I look at the code, and that's never ever what it looks like. Because we all know we need a services layer too, of course, right? So we can stuff some business logic in there. And then, of course, we need a repository layer. And the reason we need a repository layer is, I don't know. I've never seen any use for it, so let's call it a best practice. And then below that, we might have an object relational mapper, so we don't have to access the SQL directly, and then maybe we have some SQL at the end. And in reality, we might have even more layers, right? We might have things like view helpers and whatnot. So it's not uncommon that you see 10, 11 different layers. Now, when I do an architectural analysis, what I do here is that I aggregate all contributions to all files within each layer, consider each layer a logical component, and then I calculate temporal coupling on that level. Now, what do you think the temporal coupling looks like in a layered architecture? Usually something like this. In fact, I've found that somewhere between 30 to 70% of all commits tend to rip through the entire architectural stack. And this is pretty fascinating, because what's the main motivation behind a layered architecture? One thing I always heard was that it's a separation of concerns. And it is. But it's a separation along technical concerns. Each one of those represents a technical building block. However, the work that we do tends to be feature-oriented, tends to be end-user driven. And that is at conflict with the technical architecture. And the consequence is that few changes are local. Most of our changes ripple across the architecture. Now, a layered architecture like this might work really well for a small team. I've seen it work well. I think the main problems I've seen starts once the organizational size is a little bit bigger. Let's say you have maybe just 10, 12 people working on an architecture like that. What happens now is that you run into a bunch of different coordination problems, because suddenly all developers need to work in all parts of the code all the time. And this is something we're going to come back to in a few minutes. But I like to point out, and I think that this failure to separate around end-user requirements and features is one of the main motivations and one of the main reasons why microservices have become so incredibly popular over the past years. So let's have a quick look at microservices. So, as we all know, this is what microservices always look like in PowerPoint. In reality, they tend to be much more complex, right? So we might have shared building blocks. We might have service templates, client APIs, cross-cutting concerns like monitoring and diagnostics, and so on. So all that extra complexity puts us at risk for one of the cardinal sins of microservices. And one of the cardinal sins of microservices is tight coupling. The moment we start to couple different services to each other, we lose most of the advantages of microservice architecture and are left with an excess mess of complexity. So, if we have a fundamental architectural principle like that, why don't we measure and supervise it? So, temporal coupling works really well for that purpose. So all you have to do is, again, aggregate all contributions that belong to each service and calculate temporal coupling between different services. In particular, you want to watch out for patterns like this, where multiple services tend to be changed together over time. If you use temporal coupling like this, you might be able to get an early warning that can help you prevent what I call the microservices shotgun surgery pattern. Now, the microservices shotgun surgery pattern, that's basically when you want to tweak a single business capability and you end up modifying 5 different services. And there are several reasons why that happens. The most common reasons I have seen out in the wild is that, first of all, different services might share code that itself isn't stable from an evolutionary perspective, so changes to that shared code ripples to other parts. Services may also be leaky abstractions. So that means that other services come to depend upon implementation details, and they get coupled in time. Finally, I've seen that this is a more common problem when the same team is responsible for multiple related services. Now, before I move on, I would like to show you what kind of tools I use to do this analysis in case you want to try it on your own code. This is still a young and evolving field. When I started out with these analyses, was like maybe almost 10 years ago, there weren't any tools available that can do the kind of analysis I wanted to do. So I put together an open source tool suite called CodeMath. It's still available on my GitHub account. I still maintain it, and it might be a good starting point. What I'm working on right now is a product called CodeScene. CodeScene is free to use for open source projects, so if you like these techniques, please have a look at it. There are also several good tools from the academic space. So one of my personal favorites is something called Evolution Radar, which is really, really strong on temporal coupling. And then finally, in case you want to build your own tools, I recommend that you have a look at the Moose platform. So the Moose platform is basically a framework, a platform for building software analyzers. And Moose platform is also a great excuse to learn to program in Smalltalk. Wonderful language, really. Now, what I wanted to show you now was that hotspots scale to an architectural level. And we have also introduced the concept of temporal coupling that may help us evaluate and supervise our architectural patterns. Now, I want to cover the final segment in this presentation, where I want us all to explore the social side of our codebase. Let me start by asking you, how many of you in your day job, develop software as part of a team? So that's like as close to 100% as it gets. Cool. Most of us do that, right? We have to do that because we keep on taking on larger and larger and more complex problems, and we cannot do it alone, so we need to get together in order to get things done. However, what we rarely talk about are the costs of teamwork, because there is always going to be a cost. And this cost is something that social psychologists refer to as a process loss. Now, process loss is a concept from social psychology that social psychologists have taken from the field of mechanics. And the idea here is that just like a machine cannot operate at 100% efficiency all the time due to things like friction and heat loss, neither can a team. There's always going to be a cost. And that cost is called process loss. So we see an example here where we have a bunch of individual contributors, and together they have a potential productivity. That's never ever what you get out of a team. The real productivity is always smaller, and part of the potential is simply lost. Now, what kind of process loss is it? Well, it depends on the task, but if you take something like software where we have complex interdependencies between different parts of the work, you would see that most process loss is typically communication, coordination, and motivational. And another common reason for process loss is a concept called diffusion of responsibility. So, before I talk about diffusion of responsibility, I need to warn you that I'm going to talk about a really controversial topic here. It's that kind of topic you don't even mention it, right? You're not supposed to talk about it at conferences. But I need to go there. So sit tight, because I'm going to talk about code ownership. Yeah, I'm going to do that. So I just want to point out, when I talk about code ownership, I don't mean ownership in the sense that, hey, this is my code, stay away. No. I mean ownership in the sense that someone takes a personal responsibility for the quality and the future of a piece of code. The reason I think that is important is because of this principle, diffusion of responsibility, which is another idea from social psychology. And the diffusion of responsibility is something that you can see in the real world in case you are unfortunate enough to witness an accident or an emergency. Because it turns out, the larger any group of bystanders, the less likely that any individual will offer help. So this is actually quite scary. And there are several reasons for the diffusion of responsibility. One of the main reasons is because in a large group, we don't feel a sense of personal responsibility, and we just assume that someone else will help instead. And I'm pretty sure that this should be a driving principle behind good code too. In good software, I'm pretty sure you have a sense of personal responsibility for everyone involved, and I don't think there's any way around it. Now, if we have an important principle like the diffusion of responsibility, how can we measure it? Oh, it's easy. Remember, we were in version control wonderland. So our version control system knows exactly which developer that worked on which part of the code. So we just aggregate individual contributions into their teams. And from there, we can measure the overlap between different teams in the codebase. So this is the same kind of visualization that we used for the hotspots, only now the color carries a different meaning. So the color signals the amount of potential coordination between different teams. So the more separate teams that work in each part of the code, the more diffuse their contributions, the more red that part of the software. Now, once you identify parts of the code that looks like this with a high amount of diffusion of responsibility between different teams, you need to react to that finding. And the bad news here is that it's usually pretty hard. In practice, there are typically two things I've seen work. The first thing I do when I identify code like this is that I look at it from a technical perspective. And the reason I do that is because you will find out that code typically changes for a reason. And the reason that part of the code attracts contributions from multiple different teams is typically because it has good reasons to do so. It has too many responsibilities. So simply identifying those different responsibilities and starting to split the code according to those responsibilities will increase the cohesion of your solution and provide natural boundaries for the different teams and help you minimize the organizational coordination needs in your codebase. A second quite common case that I've found is that sometimes organizations need to introduce another team to take on a shared responsibility. So sometimes you might find that there's a team missing. Now, using social data like this, we can take it a step further and actually start to measure things like Conway's Law. How well aligned are we as an organization with the code we build? So it's the same visualization style, but now each color represents the contributions of each team. So this makes it possible to see things like this, which is actually quite unique, right? From the perspective of Conway's Law, if you look at this, you see that each team pretty much have their own module where they can work in complete isolation with the minimum of overhead. This is wonderful, isn't it? It's also a lie. Because I have to make a confession here. All data you have seen so far are from real-world systems, except this one. I had to make it up because I'm yet to find an organization that's that well aligned with the code. And I'm not even sure you want to be that. So I want to show you one more realistic example from a real-world system, because this is a common pattern. So this is a story about a company that decided they wanted to introduce feature teams. So what they did was they took their existing organization and sliced it into 12 separate feature teams. They worked in sprints, so at the start of each sprint, each team were given a number of tasks and then let loose on the code base. And what you see here is the contributions of the different teams over just a single month. Now, do you see any patterns there? You have to look really, really deep. And I mean, there's might be one or two components that are, almost, but not really in the hands of a single team. What you have here in general is true collective chaos. You have 12 teams that work in the same parts of the code all the time for different reasons because they work on different stories. Not only is this going to be incredibly expensive to coordinate, it's also a missed opportunity because what will happen here is that you will miss synergies between different features. That is an opportunity to simplify both the solution and the problem domain. So please align your architecture and your organization. Your code is going to thank you for it. Now I'm almost done, and I hope you enjoy this journey through the field of evolving code and behavioral code analysis. So ultimately, it's all about writing better software. Software that's able to evolve and withstand the pressure of new features, novel usages, and changed circumstances. And writing code of that quality is never going to be easy. So I'm pretty sure that we need all the support we can get. And I hope this introduction to behavioral code analysis using a crystal ball has inspired you to investigate the field in more depth. And to help you get started, I put together a number of references here. I have a brand new book on this, came out just the other week, where I go into all these analyses in much more detail. Then I also blog about it, so check out mpr.com where I present a bunch of different case studies from real-world systems. And finally, in case you want to play around with CodeScene, it's located at codescene.io. And now, before I leave a few minutes for questions, I would like to take this opportunity and say thanks a lot for showing up this morning, thanks a lot for listening to me, and may the code be with you. Thanks. Thanks. So if the tooling is for... Yes, it does. It does. So that's quite fascinating, right? Because version control data itself is language neutral. So basically, this analysis works on any kind of content that you have in version control. The only thing that is language specific, that's when you want to start to measure things like code complexity. As long as you go with simple metrics like calculating lines of code, you can get really, really far without having any language specific tooling at all. It's also fascinating to note that since it's language neutral, you might find really, really interesting patterns. So one of my favorite examples is, do we have any .NET developers here? Any .NET developer? 1, 2, wow. Oh. All right, so I used to be a .NET developer too, so there are 3 of us, right? Yeah. So anyway, the rest of you might be familiar with Microsoft's Roslyn system. It's a compiler platform where they implement 2 compilers themselves, Visual Basic compiler and a C# compiler. Now, if you do a temporal coupling analysis of Roslyn, you will find that you have temporal coupling between the Visual Basic parts and the C# parts, because they pretty much mirror each other's design. So I find it really, really fascinating, because you cannot see that in the code itself, but you can see it in the version control data, that when you do a change here, you also have a change over here. And that makes it really, really useful as a way to explore and learn the system. So it's something I think will grow in importance now that our systems become more and more disconnected with more and more complex interrelationships, like microservices. So, one more question? Yes, please. So basically the question is, once you have a hotspot, how do you know the reason for that hotspot? Is it due to changes in requirements, something external, or is it because the code quality isn't good, so you need to do a lot of bug fixes? And basically, you cannot decide from version control data alone. So that's why I always tell that version control data, it doesn't really replace anything. It doesn't make any decisions for you, but it gives you a decision basis by pointing your attention to the parts of the code that are needed the most. What I have been working on over the past years is to integrate other data sources to help make that distinction. So one thing I've been doing is to integrate with things like Jira, for example. So we can pull out information about the different tickets and find out, all right, you can connect that to the commits in case you have reference a Jira ticket in the commit. And then you can answer questions like that. All right, so this JIT packet changes because of changed hardware requirements, for example. So it might give you additional information. So I think we have time for one more quick question. Know that you want to have your coffee break. We're in Vienna after all. Yes, please.
You were showing the relation between hotspot and codebase, that would be line of code or whatever. But if, let's say we take the big file and we split in 100 small files, the hotspot kind of disappear, but I'm not sure if it's a good thing or not.
Yeah, so this is a question I actually get plenty of times. And my answer is always that, yeah, if you take a big file, first of all, we can basically game any metric we want. And if we take a big file and we slice it at random in different parts, are we going to get a better design? No, it's going to be worse. But one of the most common reasons that code grows into hotspots is because it has too many responsibilities. That's why it keeps extracting changes. So what you do is you identify those different responsibilities. Let's say you have this hotspot and there are 3 different areas. If you break apart those responsibilities, you get better cohesion. You might still have the same complexity in the code, but I'm going to argue that it's going to be easier to work with just by separating those different parts, because now the names of your different classes will provide an additional entry point once you read and explore the code. So I think that separating along the true behaviors is going to help you. Separating at random is going to make it worse. All right, so I'll be hanging around for the rest of the day, and I'll be really happy to discuss this. And vielleicht könnte ich auch auf mein Deutsch üben. Vielen Dank.